Hello everyone, welcome to the lecture series on computer architecture and organization. So in this we are going to see about the introduction to multiprocessor network topologies. So in the previous sections we discussed about this multi-core chips that require on-chip networks to connect the cores together, and clusters require this local area networks to connect the servers together. And this section reviews the pros and cons of different interconnection network topologies. Network costs. So that network costs that include the number of switches, the number of links on a switch to connect to the network, the width, that is the number of bits per link, and the length of the links when the network is mapped into silicon. For example, some cores or servers may be adjacent and others may be on the other side of the chip or on the other side of the data center. So network performance is multifaceted as well. It includes the latency of an unloaded network to send and receive a message, the throughput in terms of the maximum number of messages that can be transmitted in a given time period, and the delays that caused by contention for a portion of the network, and variable performance that depends on the pattern of communication. So another obligation of the network may be fault tolerance, since systems may be required to operate in the presence of broken components. So finally, in this era of this energy limited systems, the energy efficiency of different organizations may trump other concerns. Networks are generally drawn as graphs, with each edge of the graph representing a link of the communication network. So in this figure, in this section, the processor memory node is always represented as a black square and the switch is shown as a colored circle. We assume here the links are bidirectional, that is, the information can flow in either direction. All the network consists of switches whose links goes to processor memory nodes and to other switches. The first network that connects a sequence of nodes together, here we are seeing, is a topology which is called as a ring. Since some nodes are not directly connected, some messages will have to hop along these intermediate nodes until they arrive at the final destination. Unlike a bus, a shared set of wires that allows the broadcasting to all the connected devices, this ring is capable of many simultaneous transfers. Because there are numerous topologies to choose from, performance metrics are needed to distinguish these designs. Two are popular. The first is the total network bandwidth, which is the bandwidth of each link multiplied by the number of links. This represents the peak bandwidth. For the ring network above, with P processors, the total network bandwidth would be P times the bandwidth of one link. The total network bandwidth of a bus is just the bandwidth of that bus. And the bisection bandwidth, to balance this best bandwidth case, we must include another metric that is closer to the worst case, which is this bisection bandwidth. This metric is calculated by dividing the machine into two halves. Then we sum the bandwidth of the links that cross that imaginary dividing line. The bisection bandwidth of a ring is 2 times the link bandwidth. It is 1 time the link bandwidth for the bus. If a single link is as fast as the bus, the ring is only twice as fast as the bus in the worst case, but it is p times faster in the best case. Since some network topologies are not symmetric, the question arises of where to draw the imaginary line when bisecting the machine. Bisection bandwidth is a worst case metric, so the answer is to choose the division that yields the most pessimistic network performance. We can state alternatively this as calculate all the possible bisection bandwidths and pick the smallest. We take this pessimistic view because parallel programs are often limited by the weakest link in the communication chain. So at the other extreme from a ring is a fully connected network where every processor has a bidirectional link to every other processor. For fully connected networks, the total network bandwidth is P into P minus 1 divided by 2 and the bisection bandwidth is P by 2 square. The tremendous improvement in performance of fully connected network is offset by the tremendous increase in cost. This consequence inspires engineers to invent new topologies that are between the cost of rings and the performance of fully connected networks. The evaluation of success depends in large part on the nature of the communication in the workload of parallel programs that run on the computer. So there are a number of different topologies that have been discussed in publications which would be difficult to count, but only a few have been used in commercial parallel processor, and this illustrates one of the two popular topologies. If you see here, the colored circle in this figure that represents the switches and the black square that represents the processor memory nodes. Even though a switch has many links, generally only one goes to the processor. The Boolean n-cube topology is an n-dimensional interconnect with two n nodes requiring n links per switch, that is plus 1 for the processor, and thus n nearest neighboring nodes. Frequently, these basic topologies have been supplemented with extra arcs to improve the performance and reliability. An alternative to placing a processor at every node in a network is to leave only the switch at some of these nodes. The switches are smaller than processor memory switch nodes and thus may be packed more densely, thereby lessening distance and increasing performance. Such networks are frequently called multi-stage networks to reflect the multiple steps that a message may travel. So there are types of multi-stage networks or as numerous as the single stage networks. So this figure illustrates two of the popular multi-stage organization. So in this figure, if you see, this is one type that is crossbar network and another one is omega network. So this crossbar network is also called as fully connected network, which allows any node to communicate with any other node, that is in one pass through the network. An omega network uses a very less hardware than the crossbar network, that is it is lessened by 2n log 2n versus n squared switches, but contention can occur between the messages depending on the pattern of communication. For example, the omega network that is shown here cannot send a message from P0 to P6 at the same time that it sends a message from P1 to P4. So that's all about this network topologies. Thank you.